You are now in a vast void, where darkness completely envelops you. You are isolated, trapped in a place where even an amateur telescope can't capture any stars or galaxies. To you, the universe seems empty. This is the Boötes void, a spherical region with a diameter of 330 million light-years. To give you an idea, the Milky Way would fit inside this void millions of times. In a volume where thousands of galaxies should exist, we observe only 60. These few galaxies are spiral and blue, illuminated by the formation of new stars. Astronomer Greg Aldering said that if the Milky Way were at the center of this void, we wouldn't know about the existence of other galaxies until the 1960s. If Earth were on the edges of the Boötes void, we would see the other side of the void as it was when amphibians dominated Earth, before even the dinosaurs. But how can such a void exist? The age of the universe sets a limit for the size of any structure, but the Boötes void breaks that limit. It gives us a glimpse into the growth of structures in the early times. The few galaxies observed within the void follow a tubular shape, perhaps the remnants of a wall between two voids. Even here, in the Great Nothing, one of the darkest places in the universe, there is the light of galaxies, revealing their secrets through the visible spectrum. To find true darkness, we have to look beyond the Boötes void, further back in time. Only in the cosmic dark ages, before stars, galaxies, and planets existed, do we find complete darkness. For about 200 million years after the Big Bang, the universe contained all the ingredients to form the first stars, but none formed. There was no visible light. But why did the cosmos remain dark for so long? What does this mean for the stars and galaxies we see today? And how can we shed light on an era where there was only darkness? In 1543, Nicholas Copernicus showed that Earth is not the center of the solar system. In the 1920s, Jan Oort discovered that the Sun is not at the center of our galaxy. And in the same decade, Edwin Hubble revealed that our galaxy is just one among countless others. Cosmologically, we are the center of nothing. And that is an unsettling realization. In 1995, Bob Williams, then director of the Hubble Space Telescope, decided to use observation time for something special. He pointed the telescope at a tiny patch of sky, just 1/30th the diameter of the Moon, and left it there for 10 days. The result was one of the most iconic images in astronomy, the Hubble Deep Field. It revealed distant galaxies of all sizes, shapes, and colors, showing us a universe teeming with life. But like any photograph, this image is a 2D projection of a 3D landscape. Very distant galaxies appear as neighbors. It is also a projection of time. Photons from the farthest galaxies traveled for longer, so we see these galaxies as they were billions of years ago. To understand better, we can consider the observable universe as a series of shells around us. The more distant the shell, the older the photons we receive, allowing us to see further back in time. Edwin Hubble observed that the farther a galaxy is, the faster it seemed to be receding, a cornerstone of the Big Bang theory. By measuring the redshift in a galaxy's spectrum, we can calculate the speed at which it is moving away from us. This way, we can separate the thousands of galaxies that seem tangled in deep field images and peel away layers of young galaxies until we are left with the oldest, the first of their kind. The latest image from the James Webb Space Telescope, JWST, covers an area of the sky the size of a grain of sand, and even so, thousands of galaxies emerged from the darkness, pushing the cosmic frontier to just a few 100 million years after the Big Bang. We are finally reaching a moment in the universe where there was no visible light, a time that even the JWST cannot see, the frontier of the first stars. But does that mean we can't go further? Are we forever closed off from the darkness that existed before? At first, light dominated the universe. After about 380,000 years of expansion, the energy density of radiation had fallen below that of matter, and the dominance of light in the cosmos ended. The temperature of the plasma had cooled enough that atomic nuclei could now reliably combine with electrons into simple atoms. Although light was no longer the dominant force in the universe, there was a silver lining. The creation of atoms now meant photons had space to travel. To an observer, the universe would have appeared to have a warm orange glow. Over the next 100 million years, as the universe expanded further, cooling temperatures caused this glow to become more reddish over time. Finally, it cooled so much that no radiation was emitted in the visible part of the electromagnetic spectrum. The embers of the Big Bang faded entirely into the infrared, microwave, and radio wavelengths. Darkness fell. In the midst of the darkness, however, all was not quiet. Another type of matter was created in the Big Bang, a type of matter that is still mysterious to us today: dark matter. In the 1960s, scientists Kent Ford and Vera Rubin measured the orbital speeds of stars in spiral galaxies and found that something didn't add up. The orbital speed of the stars was too high for the visible mass of the galaxies. There must be a hidden mass component keeping them in orbit. This hidden mass was called dark matter. Dark matter makes up 4/5 of all the matter in the universe, but evades our direct detection. It cannot absorb or emit photons, and thus leaves no mark on a spectrum the way chemical elements do. It does, however, have a gravitational force, and thus areas of high dark matter density can grow and collapse through accretion. But dark matter cannot form stars or planets. It collapses into filaments, connecting at their densest points into halos. Unable to emit light, our observer from the Big Bang could not see this vast backdrop network of dark matter. And so, during the dark ages of the universe, we know that the darkness was not empty. There was structure at play behind the scenes, a web of dark matter that drew in nearby hydrogen and built the foundations of the universe brick by brick. And throughout the universe, about 200 million years after the Big Bang, gravity would crush these dense pockets of hydrogen just enough to ignite the engines of stars. In all directions, the lights turned on, slowly illuminating the dark ages. But was the darkness that preceded this visible illumination truly devoid of light? Despite emitting across the electromagnetic spectrum, the first stars found their initial cries muffled by the darkness of a vast hydrogen ocean. The path was not completely clear for this new light. When the first fusion engines began running, and the resulting photons struggled to escape from the core to the surface of the star, they encountered clouds of atoms ready to absorb them before they could travel much further. It didn't take long for these first stars to begin changing their surroundings. The highest energy level in a hydrogen atom is 13.6 eV2. This means that 13.6 electron volts, eV, is the amount of energy needed to remove the electron from the hydrogen atom, i.e., to ionize it. If the atom absorbs a photon with more than this amount, the electron overcomes its bond with the proton and becomes a free particle. The hydrogen atom is said to be ionized. Immediately after the Big Bang, the high temperatures and frequent collisions rendered all normal matter ionized. But soon after the end of the Dark Ages, the era of reionization began. The first photons from a first star, and later from a first galaxy, ionized their immediate surroundings, creating a sphere of ionized hydrogen through which subsequent photons could travel a bit further before encountering an intact hydrogen atom. Over time, these bubbles of ionized hydrogen grew larger and larger, connecting and merging so that the hydrogen gas we observe around us today is almost entirely ionized. Thus, a billion years after the Big Bang, in a universe full of ionized gas, light could travel as freely as it does today. The epoch of reionization was complete, and with it, the Dark Ages truly ended. Along with the Dark Ages, the epoch of reionization is a nearly absent era in the timeline of our universe's evolution. To be continued in the next episode.